Okay, in this video tutorial we're going to look at osmosis. So before we get into that, I'm just going to introduce a couple of new terms. The first one being water potential. So water potential is the tendency of water to move down its concentration gradient. It's the potential for water to move from high concentration to low concentration. So we say that water always moves from a region of high water potential or high water concentration to an area of low water potential or low water concentration. So it's a little bit depends on what curriculum or country you're studying in. The Cambridge curriculum seems to prefer that you say moves from a high water potential to a low water potential rather than using the word concentration. But both are essentially used. So equilibrium is reached when the water potential is the same on both sides. And so that means there will be, by definition, equilibrium means there's no net movement, in this case of water. So there may still be some water molecules moving each way, but overall there will be no more moving in one direction than in the other. So solute potential is basically the concentration of solutes in the solution. So pure water has a water potential of 0. When you add solutes, that lowers the water potential, so that so all solutions, anything that's got some solutes in it, have a negative water potential. So you never really get positive water potentials. Pure water has a water potential of 0. And if you add solutes to that water, it becomes negative. So solute potential is always a negative value. It reduces. Adding solutes to the water makes the water less pure. It reduces the water potential, makes the number more negative. So if we ignoring plant cells at the moment, because the cell wall and turgor pressure and things like that come into play, and we'll look at that a little bit later. But if we look in a regular cell, basically solute potential and water potential are the same thing. So pure water has a water potential of 0. If I add a certain amount of solutes, that's the solute potential would be the concentration of solutes I've added. Essentially is subtracted, it's a negative value, and then the water potential will have that negative value as well. So unless you've got a cell wall that can constrain the volume of a cell and things like that, essentially water potential and solute potential are the same thing, or will have the same value. So just a slight difference in definition there. Water potential is the potential for water to move down its concentration gradient, and solute potential is essentially the concentration of solutes in a solution. And it essentially, if there's nothing else acting on the water, no pressure being applied or cell wall, then the solute potential essentially is what determines the water potential. So if I add salt to a beaker of water, the solute potential, it'll be a negative solute potential. The more salt I add, the more negative that solute potential, and the water potential will be exactly the same negative value. So in that instance, water potential and solute potential, the values are the same. So this is where we get to osmosis. Osmosis is the movement, the diffusion of water molecules from an area of high water potential to a region of lower water potential through a partially permeable membrane. Now, again, Cambridge prefers partially permeable. When you get to university and things, or if you're doing NCA, you'll often see them use the word semi-permeable rather than partially permeable. So just worth noting that. So diffusion of water from an area of high water potential to a region of lower water potential through a partially permeable membrane. So that's what we're trying to show here. We've got a beaker, and it's full of, we've got some water in here, and we've got a membrane, but it's partially permeable. There are some gaps so that some solutes, some things or molecules can move through the membrane. So in this case, we're going to pretend that these yellow dots, these yellow molecules, are just slightly too big, that they can't fit through these pores, which means that they can't transverse the membrane. And we're going to say maybe they're too big, or maybe they're polar, so they can't squeeze directly through the membrane, through those phospholipid, especially that lipid fatty layer. They can't get through the membrane either. So the yellow solutes, in this case things that are dissolved in the water, are stuck on this side, and the ones that are on this side are stuck on this side. So we're not going to get any movement of our yellow molecules here, of our solute here. But water can move down its concentration gradient. So in this case, we've got a higher concentration of water, or a higher water potential on this side than we do on this side. So we've got a higher concentration of water here than here. That means we've got a higher water potential on this side than we have on this side. So if we think of if we had pure water on both sides, the water potential would be 0. But when we add some solutes, the water potential will come down. So the solute potential on this side might be -4. I'm just saying that because we've got 4 molecules. So we might have a solute potential of -4. And that means that the water potential will be -4 as well. Whereas on this side, the water potential here, pure water would be 0. How many little yellow dots do we have? Maybe about 20. So the water potential here might be -20. So it's a lower water potential, a lower concentration of water. So the solute, even though it's expressed as a negative value, so the more solute we add, the more negative the solute potential, is basically saying how less concentrated the actual water is. So we've got a lower water potential on this side, or a higher water potential on this side, or a higher concentration of water, and a lower water potential on this side, or a lower concentration of water. So really those values, we use that symbol, the little psi symbol. Sorry, let me grab a pen. So on this side we might have a water potential might be, say, -4. Now normally you wouldn't actually get values that high. Normally they're 0 point something, but we'll just go with that for now. And so the solute potential is actually, so just with a little s, is actually -4 as well. So unless we're talking about a pressure being applied, or membranes, cell walls and things in plants, it's always the same. Whereas on this side we might have a water potential of -20, and the solute potential is -20. So think of it as pure water is 0 minus the solute potential, or factoring in the solute potential, which is a negative value, gives you the overall water potential. So because the solute potential is -4, that means that in this case the water potential has become -4 also. On this side, because the solute potential is -4, the water potential has also become, -20. The water potential here has become -20. So this negative value, you can think about how impure the water is becoming. So here we've got a few solutes added, the water has become less pure, less than 0. And here we've added a lot of solute, it's become a lot less pure water, which means that we've got a much lower value. So -4 is a higher number than -20. We've got a higher water potential here than we do here. And that takes, some students takes a little bit of getting used to, getting their head around that. The idea that this is a bigger number, or of greater value than this number. So when you're dealing with negatives, remember, the closer to 0 you get, the bigger or the higher the number actually is. So higher water potential on this side than on this side. So osmosis is the movement of water down its concentration gradient from an area of high water potential to an area of lower water potential. The solute potential is basically how much solute we've added. It's not actually the number of molecules. It's not, you can't equate the number directly, but it's a measure of, so the solute potential is a measure of the number of solutes added. It's a negative value, and that is one of the factors that determines our water potential. So in this case, because nothing else is affecting water potential, -4 solute potential means our water potential is also -4. Okay, so in an example, in a plant root here, there's a lower concentration of water in the cell than in the soil. So water moves out moves into the root hairs, so out of the soil and into the root hairs through osmosis, resulting, it says there, in a hypertonic solution. We'll talk a little bit about that later. But essentially there's a higher concentration of water, or a higher water potential outside the root hair, so water will move into the root hair, into an area of lower water potential. And why would there be a difference there in the water potentials? Because inside the root there will be more solutes, so more things dissolved in the water in here. It won't be as pure, and so that will have a more negative value. Then the water around the root will be relatively pure, or almost pure. It will have a higher value, not quite as negative a water potential. So osmosis is a form of passive transport as well, so this doesn't require energy, but it involves the movement of water rather than other substances, and it's always across a partially or semi-permeable membrane. So we can have three different types of solutions. A hypertonic solution is when hyper meaning lots, tonic meaning essentially the number of solutes in there. So this is a solution with a lot of solutes. So if we put a cell, so you can imagine this circle here is a cell, in a hypertonic solution, it means that the concentration of dissolved substances is higher outside the cell. So maybe we've got lots of salt, really salty water out here, lots of dissolved substances, lots of solute, and that's going to cause water to diffuse out, because the water, say if the water in a cell was pure, it's never quite pure, but if the water inside here was pure, that would be a water potential of 0. And out here, because we've added solute, maybe this has a water potential of, negative 0, a solute potential of negative 0.4. So with a little s there, the solute potential is negative 0.4 because we've added solute. And that actually means if no other factor is affecting the water potential here will be negative 0.4. So you can see then that the water potential is higher here, so water will move from an area of higher water potential to an area, if this is a negative value, so to an area of lower water potential. So a hypertonic solution means the concentration of dissolved substances, the solute potential in the surrounding solution, is higher than the concentration of dissolved substances, the solute potential inside the cell. So we've got a higher solute potential, a greater solute potential, as a negative value, more solutes out here than inside the cell. So this causes water. So essentially there's less water. Now it's not less by quantity, but a lower concentration of water outside the cell than inside, and so water will flow out. So if you place an egg in salt water, it will shrink. So if you dissolve the shell with a bit of vinegar and then place an egg in salt water, it will shrink very slightly because water leaves the egg. But you do need a very salty solution for that. So hypertonic, lots of solutes in the solution around the cell, lots of solutes in here. So you'll have a more negative solute potential, or a lower water potential. So water always moves out from an area of higher water potential to an area of lower water potential. Hypotonic is the opposite. Hypo is a low. So I think hypothermia is when your temperature gets too low, you get too cold. So that's saying that in the solution outside the cell, we have less solute molecules. So maybe in this case we could say we've got pure water outside the cell. We've got less solute molecules than there are inside the cell. So you can imagine in this instance we've got some salts dissolved inside the cell, but pure water around the outside. So hypotonic means a lower solute concentration on the outside of the cell. So in this case, if we've got pure water on the outside, this would have a water potential of 0. Whereas inside the cell now, we would have a solute potential that's a negative value based on how many molecules we have in here, so maybe 0.6. I'm just making that up. And if there's no other factor affecting the water potential, then the water potential, sorry, I should draw the little symbol there, so that's the solute potential. The water potential would also be negative 0.6. And again, this means that water moves from, it's a higher water potential here than there is inside the cell, so water will move into the cell. So a hypotonic solution is when the concentration of dissolved substances, or that solute, the concentration of solutes in the surrounding solution is lower than the concentration of dissolved substances inside the cell. We have more solutes dissolved inside the cell. So therefore there is more water. Again, that's not quite right. There's a higher concentration of water outside the cell, and so water will flow into the cell. So a good example of this is when you take a saltwater fish and you place it in fresh water. There's a higher concentration of water outside of the fish, so it swells up and usually dies. Okay, isotonic. So an isotonic solution is when the solute concentration outside the cell is the same as the solute concentration inside the cell. So they could both be 0, or we could have a solute concentration of, here of negative 0.5, and we could have inside a solute concentration of, again, negative 0.5, for instance. So in this case, if the solute potentials are the same, and here this means that the water potential would be 0.5 here, and negative 0.5 here, and negative 0.5 here. If the water potential is the same, there's no net movement. And what that means is that there's the same amount of water molecules moving in as there are out. So there is still some movement of water in and out, but there's no net movement. The overall is there's just as much coming in as there is going out. So it's a type of osmotic solution in which the concentration of dissolved substances in the surrounding solution is the same as the concentration of dissolved substances inside the cell. So there's an equal flow of water in both directions. So isotonic, equal flow of water in both directions. So when blood cells are placed in a 0.9% salt solution, they neither gain or lose water as the cell stays the same size. So if we just summarize those, isotonic, solute concentration the same on inside and outside the cell, so no net movement of water. Oh, sorry, I need to go back. Hypotonic, we've got less solute outside the cell than inside the cell, less solute outside the cell, which means there is a higher water potential. The water is more pure outside the cell. So if we've got less solutes outside the cell, we've got more pure water. The water outside the cell is more pure, or higher concentration of water, so a higher water potential. Hypertonic, we've got a solution that has more solutes dissolved into it, so less pure water or less concentrated water, which means the water potential is greater inside the cell and it will move out into that solution. So if we talk quickly just about what effect that has on cells, essentially if we look at plant cells, if it's a hypotonic solution, water moves in and the cell will burst or lyse. If it's an isotonic solution, in both cases a cell will be normal because you'll have no net gain or loss of water. If you put an animal cell, like a red blood cell, into a hypertonic solution, so one where there's a lot of solutes around in the solution, a lot of solutes means a lower water potential, so water moves out. The cell shrivels, so it reduces in volume, and it can become crenated. The word crenated is a description of the shape of the cell. Because of its contents, it often becomes sort of slightly spiked or star-shaped, and we say the cell is crenated. So it reduces in volume or shrivels. If a plant cell is put in a hypotonic solution, it doesn't burst, and the reason for that is there is actually outside of the membrane there's that cell wall. And the cell wall is that cellulose kind of network, and that acts as kind of almost like a net that's covering the cell, which restricts its volume, so that the cell can't expand beyond a certain volume, and that stops it from bursting. So if water continues to pile in there, the pressure inside simply builds up, and we'll talk about that in the next video. So lastly, if the if a plant cell is placed in a hypertonic solution, so a solution with lots of solutes, lots of solutes means a low water potential, so the water rushes out, and instead of just shriveling, what happens is the cell wall retains its shape, and so the cell membrane pulls away from the cell wall and is teared. Because the cell wall is often joined at certain points to the cell membrane is joined to the cell wall at certain points, as it shrivels and pulls away, it often rips off. So the membrane pulls inwards and is ripped off the cell wall, and we call that plasmolysis. Or we say that the cell has plasmolysed. Plasmolysis, or we say the plant cell is plasmolyzed. So that's the idea of osmosis. It's always about water moving from an area of high water potential, or where the water is most concentrated, where we have the least solutes, to an area where we have a lower water potential or more solutes. So osmosis, just to define it again, is the net movement or diffusion of water from an area of high water potential to an area of low water potential, or you could technically say an area of high water concentration to low water concentration across a partially or semi-permeable membrane. So just a few different countries kind of using different terms there. In Cambridge, they prefer you to, if you're doing a Cambridge curriculum, they prefer you to use the word water potential rather than water concentration, and a partially permeable membrane rather than a semi-permeable membrane. Cool, so that's osmosis. This video is probably a bit of a tricky one to get your head around, so you might want to watch it another time, but I hope you found that helpful.